So how did we get from this very, very uniform state, which occurred about 300,000 years after the Big Bang, to all of this delicate, complex, beautiful structure of planets and stars and galaxies that we see today? The main motor of all of that structure formation is, again, gravity. Gravity works to draw things together. So even these slight fluctuations in density after the Big Bang become larger and larger as the more dense places attract matter into them, and all of the matter tends to collapse into these dense regions, forming stars. The stars collect together into galaxies. The galaxies collect together into galaxy clusters, and you get this tremendous variation in complexity simply by the operation of the simple law of gravity from an extremely uniform looking initial state. That's the modern story of structure formation, and it's been worked out in great detail. What you do now is you can't test this in the laboratory, so you test it on computers. You put into the computer the laws of gravity and various initial states, and you let it evolve in time and see what kind of structures form. Now, in order to get the predictions to match what we see, an extra ingredient has to be added, which is called dark matter. There seems to be more gravitating matter in the universe than the matter that we can actually observe. So whatever it is, it doesn't emit light. It's dark. It's not hot, so this is called cold dark matter. And we find that galaxies seem to have a halo of dark matter around them that account for the motions of the stars within the galaxies. This dark matter does have an effect. It has gravitational effects. It bends light. And so astronomers now look through their telescopes for these telltale effects of the gravitational light bending due to dark matter. The story about how we got from the Big Bang to the present day is on very solid ground. As far as we can go back through our telescopes is to the cosmic background radiation. We can't see beyond that, so we have to let theory take us further back toward the Big Bang. Now, what is at present the most widely accepted theory is that it didn't just happen that the Big Bang occurred and the universe expanded uniformly after that, but that shortly after the Big Bang, shortly after this initial state, there was a period of extreme expansion, inflationary expansion, the size of the universe doubling and redoubling many times extremely quickly. And then that initial expansionary phase ends, and the slower rate of expansion that was proposed by Lemaitre takes over, and that takes us up to the present day. That's very well attested by the evidence and by theory, but it leaves still open the question, what about the Big Bang itself? Is there anything more to be said about it except that it was the beginning of everything? Remember that the Big Bang, the singularity state, was originally arrived at by analysis of Einstein's equations. But Einstein's equations only deal with gravity, and gravity isn't the only physical force there is. In addition to gravity, there's electromagnetism, and there's the weak and strong nuclear forces, and those forces are all dealt with by quantum theory. It's hard to put quantum theory and general relativity together, and no one really quite knows how to do it. So we're entering the realms of speculation now and not settled physics. But indications are that putting quantum theory together with general relativity might yield an entirely different picture of the Big Bang. That instead of it being the very end of space-time, and instead of everything coming together into a point, that quantum theory will smear things out a bit, and you can imagine going even earlier than the Big Bang. You can ask questions about where the Big Bang itself came from, what was before it. And there are several theories that suggest a sort of state of the universe antecedent to the Big Bang. One of these theories is called the theory of eternal inflation, and it holds that there was a background state, again, of this rapidly inflating, expanding kind of universe that gives birth to these smaller bubble universes or pocket universes like we live in, where the expansion is much slower and more sedate. It would give rise to an infinite number of these smaller bubble universes, and we just happen to find ourselves in one of them. So you can think of the inflationary theory as a kind of scientific birth from chaos theory. Although the birth was of more than just the world we live in, there's the birth of other worlds that we can't directly communicate with. There's another idea, which is that antecedent to the Big Bang, there was another universe very much like ours that expanded and then contracted, or expanded and got into a state where it transitioned into the Big Bang, and that itself, the same story occurs. So you get a cyclic cosmology. You get a new universe that exists and then ends and gives birth to a new universe that exists and then ends over and over and over, just like in the Hindu account of the cosmos. And of course, there's always the original idea of Lemaitre that when you go back to the Big Bang, you really get to the end of everything, the end of space and time itself, and so you have a finite universe theory. So what we see is that these are the only ideas there are that people came up with in mythology and in philosophy and repeating in science, because what other possibilities are there? Our structured universe might have come from something unstructured, as in the chaos theory, or it might have come from something earlier that itself was structured, as in these cyclical theories, or it might not have come from anything, as in the finite time theories. And there's also the possibility of the steady state theory, that things have always been like this. The cosmologist Fred Hoyle had held strongly to a steady state theory in which the universe existed forever and always looked something like this. We're not really going to be able to know which of these scientific cosmologies is correct until we can work out better the theory, because what we have to go on is basically theory rather than observation in this realm. And we don't know yet exactly how the quantum theory applies in these very extreme conditions of high density and very high temperature.